So I'm going to be talking about the epistemic role of equilibrium solutions in GR. This talk could alternatively be titled something like "What Anti-Gravity in Science Fiction Contributed to the Study of Analytic Solutions in GR," which is like a kind of wonky reframing, but bear with me because it's like a quasi-historical, but I'm not a historian, so we'll see how it goes. And I look forward to your comments. Okay. So the question that I want to ask in this talk is, how do exact solutions go from being toy models to objects of study in general relativity? So there was a time in which they're kind of toy models that represent what we think about real systems, about the real universe. And then they cease to be treated merely as these kinds of idealized models. And then eventually they start to become objects of study in and of themselves, with whole books published that catalog all the kinds of exact models that exist and how to go between them, et cetera, et cetera. So there's this transition, and I want to understand better what's going on during this transition. And I'm going to tell the story in 3 parts. First is part 1, which is kind of birth and treatment of individual exact models. There's a time period, part 2, where there's a neglect of general relativity kind of as a whole, and what has been dubbed the low watermark period by real bona fide historians. So we'll talk about that briefly. And then part 3, revival, with a kind of comprehensive treatment of exact solutions emerging in the literature and discussion of new solution generating techniques that would have looked really pretty wild to the people in part 1 of the story. So I'm going to give the part 1 and part 3 through 2 specific examples. First is going to be discussions around the Schwarzschild solution for part 1. And part 3, I'm going to present one of the solution generating techniques used or presented at the time, what's called the Newman-Janis trick. But really, these are just 2 examples that are meant to show you how people are thinking differently. So first, the part 1 example is kind of an idealized model of a real physical system. And the part 3 example is as a tool for exploring the structure of a theory solution space. So these exact models, or as I'll kind of claim equilibrium solutions, you might think about them for the purposes of GR as equilibrium solutions, go from a kind of, these are idealized models, to a different kind of epistemic role in theory-based exploration. Okay, and here's the upshot. Private patronage played a non-negligible role in the changing use of exact solutions. So that's what I'm going to try and argue for you today via a little bit of history. Okay, so let's get started with part 1, birth. So I'm going to give you a very, very selective history of general relativity. So we have in 1905 special relativity, which gives us the claim that all inertial frames of reference are equivalent. In 1907, Einstein adopts the principle of equivalence as a kind of guiding principle that's going to guide his theorizing in the coming years. So equivalence of inertial and gravitational mass. So he enlists Marcel Grossmann in his quests, and together they end up publishing Antwerp theory or sketch of something like a precursor to GR. And this is good along the story, but Einstein is unsatisfied because it doesn't have general covariance. And it isn't until 1915 that Einstein will publish the field equations. This is a very selective history. Please see more references for a little bit more nuance in how this history progresses. Okay, so the field equations of GR are a coupled system of nonlinear second order PDEs, and their solutions are metrics of the whole spacetime. So exact solutions here include things like vacuum solutions, stationary solutions, static solutions. Some are fluid solutions. Here I'm going to be focusing, for the purposes of this talk, on equilibrium solutions on stationary and static ones. So stationary ones have a killing vector that's asymptotically time-like. So basically, they're kind of stationary in some way, but they're allowed to have rotations. Static ones are stationary, and they have the further requirement of no rotation. So in GR, we take these to be what we're talking about when we're talking about equilibrium solutions. So I won't really use equilibrium but in this talk, but these are the kinds of solutions that are considered to be equilibrium solutions for the purposes of GR. Okay. So what are some of these? Some of the earliest exact solutions include derivations of something like Minkowski spacetime from the GR field equation. So this is, of course, the setting of special relativity. So we have flat space with no matter or gravitational field anywhere. And Einstein, when he is deriving Minkowski spacetime in GR, he's seeing this as a kind of limiting or special case of GR. And he sees that deriving the relevant limit serves as a kind of convincing proof of the correctness of the theory. So if you don't get this in the limit, you might be more skeptical about the theory. That's the kind of intuition there. And when he's talking about this, he really thinks that it's meant to serve a kind of pedagogical role to get you on board with the theory. So he presents it in such a way that the reader will feel that the path we have entered upon is psychologically the natural one, and the underlying assumptions will seem to have the highest possible degree of security. So if we start with the familiar and we're able to get that back in the limit, we're convinced of it. Another kind of early exact solution is the static, Einstein's static universe. So in this 1917 paper, famous for being Einstein's biggest blunder, he adds this cosmological constant term that is meant to keep things really static, closed, the universe being closed and unchanging. So there's more nuance here to be said about whether or not this was a blunder or whether it was kind of justified by his wanting to get something like Mach's principle. And here I'll point to Chris Fink's paper for this. But just the general idea here is that these are early exact solutions. Both of these, though, are preceded by Schwarzschild solutions sent to Einstein shortly after he publishes the field equations in 1915, and then published by Schwarzschild in 1916. So to set the stage, where this comes from is that Einstein is interested in resolving Mercury's perihelion precession in GR. So that's one of his goals, is to derive Mercury's perihelion precession accurately. And he takes Mercury as a kind of test particle in the sun's gravitational field to derive this perihelion precession. So he wants a vacuum spacetime that's asymptotically Minkowskian in order to do this. But even Einstein doesn't actually solve his field equations fully. He linearizes them. And then Schwarzschild comes along and provides an exact solution. So the Schwarzschild solution was really meant in this early context as a kind of predictive tool, maybe, for understanding Mercury and predicting Mercury's perihelion precession. So here's the original paper, Schwarzschild, on the gravitational field of a point mass according to Einstein's theory. And then Einstein's reply to Schwarzschild's letter, which I think is just cute. He says, "I examine your paper with great interest. I would have not expected that the exact solution could be formulated so simply. After all, he didn't do it himself. The mathematical treatment of the subject appealed to me exceedingly, and he's going to deliver it before the Academy with some words." So this is the kind of early history of the Schwarzschild solution. So we're really seeing this as a predictive tool in GR and really modeling actual physical systems. Okay, so what is it? So it describes the gravitational field around a central non-rotating spherical mass. For now, it's non-rotating. We can extend it to further models later. And it has two singularities of interest. The first is the central singularity at R0, and the second is what gets called the spherical singularity in some of the literature at R is equal to 2m. So you can see that if you were to plug in 0 here and here, or if you were to plug in 2m there, you would derive these kinds of singularities. There are different interpretations of these, though. So the central singularity is thought to be a placeholder for the matter source itself. And it's not really seen as problematic because Newtonian theory also had a kind of central singularity. So no worries there. The second one is by many at this time considered to be a mathematical artifact. Pragmatically, we're restricting attention to R greater than 2m, so outside of the mass. And so this is thought to be a kind of coordinate artifact by some at the time. And, you know, Einstein famously talked about kind of coordinate artifacts. So in this letter to Penlevy, he says, "Only conclusions reached after the elimination of coordinates can pretend to have objective significance." So this objective significance won't be granted to things that are mere coordinate artifacts. Things start to change in 1922 at the Paris conference, though. And here, Hadamard asked Einstein, okay, I get that this is a coordinate artifact, but what would happen if the r equal to 2m singularity is outside of the gravitating object? So before you were thinking, okay, we're talking about the sun, and this is going to be inside of the gravitating object, but Hadamard asked, what about if it were to occur outside? And Einstein's really wary of this. He calls it Hadamard's catastrophe. And there's like really funny other kinds of terms for what this gets called. So Eddington calls it the magic circle, Becquerel calls it a hole in space, Weil calls it the gravitational radius, and Nordman calls it the death. Differing, yeah, like Weil's maybe the least creative of the approaches with naming. Okay, so the point I want to illustrate here is like they're worried about it because it's being taken as a kind of physical model. Okay, so what happens with the Schwarzschild metric? So Rieser and Nordstrom independently publish an extension of the Schwarzschild metric for charged non-rotating spherically symmetric masses. Chandaneskar and Landau independently derive mass limits for a white dwarf, so the precursors to what we'll call black holes now, before they collapse. What's the mass limit that they can get up to before collapse? And then Einstein aims to demonstrate that singularities can't occur in nature. And we know this from a paper with Rosen in 1935 that he worried singularities indicated arbitrariness. So we get a similar kind of thing to his discussion of coordinate artifacts. And then we have Oppenheimer and Schneider as in 1939 predicting occurrence of the central singularity. And here's where we kind of get to the origins of what will be taken up as black holes later. Okay. So what's actually going on here? So some are studying robustness in this history. So some people are asking whether the Schwarzschild metric can be extended to systems that have other properties besides the ones that Schwarzschild had originally. So suppose that the system has charge, what does the metric look like? What do the exact solutions look like? Others are studying plausible physical mechanisms that might result in a kind of singularity, right? That's the collapse model. And in general, of course, the exact solution is a huge idealization. So in all of these cases, this is a huge idealization of what the universe can be described as. And so we might think of some of this literature is thinking about intramodel de-idealization. So here I'm thinking like the Chandaneskar mass limit to the Oppenheimer-Schneider collapse is a kind of intramodel de-idealization. Here I'm using Eugene and Eugene's discussion of de-idealizing de-idealizations. But also we can think about Einstein's worries about the singularity as revealing that he's ascribed it a kind of physical status. And I'll just note that depending on how you want to understand what role exact solutions are playing in this story, if you think about them in relation to other approaches like topological causal analysis or initial value formulation, you can see them as all kind of doing a de-idealization together. So again, here I'll point to Eugene's dissertation work on understanding how to like combine these approaches as all giving you a kind of de-idealization. Okay, so here's my main takeaway from this part. Exact solutions are being investigated as plausible models of physical systems. So the justification is that the worries about the singularity of the Schwarzschild metric demonstrate this. If you thought that they were just artifacts of the idealizations, that's fine. But if you come up with physical processes that are going to result in these kinds of singularities, then you should be worried about them. And the fact that they're worried about them means that they are thinking of these as not just artifacts of the idealizations, but as representing real systems or something like that. Okay, so now on to part 2. So we stepped briefly into the 1930s, but let's take a step back into the time period between 1925 and 1955. So Gene Eisenstadt has called this the, quote, low water mark of relativity. And there's various quotes that kind of illustrate what the status of GR is at the time. So Bergman Tappei says, you only had to know what your 6 best friends were doing and you would have known what was happening in GR. Just your little network of people. Kannefig, in his book Traveling at the Speed of Thought, says there is an interregnum in research on GR theory that lasted a period of 30 years from the mid-20s to the mid-50s. So various historians have kind of made this claim. So why is this? What was going on? So there's a few things, and I'll kind of give the big picture story and then go into some of the details. So GR is at this time pretty hard to work with, and this comes in 2 flavors. So Eisenstadt says it's exceedingly isolated from other theories. So it's like not making the right kinds of connections to other theories that would help you want to work on it. And then this quote from Wheeler is actually in the proceedings of one of the conferences I'll talk about in third part, but he says, an objection one hears raised against the general theory of relativity is that the equations are nonlinear and hence too difficult to correspond to reality. I'd like to apply that argument to hydrodynamics. Rivers can't flow in North America because the hydrodynamical equations are nonlinear and hence much too difficult to correspond to nature. So he says, all of you people who think that this is too hard, suck it up. Like maybe it is really difficult and maybe that's just what models reality. And so that shouldn't be a good excuse. Okay, so GR hard to work with. Another reason that people aren't really working on it is that it's not actually providing empirical predictions at the time. So there were 3 initial, classical tests of GR: Mercury's perihelion, gravitational redshift, and gravitational lensing. But beyond those 3, applications of GR at this time are largely cosmological. A lot of cosmologists have started working with it, but there's not a lot of like on the ground tests or even solar system tests beyond these 3. So Eisenstadt says that GR is delivering too small a number of empirical predictions in comparison to the efforts to work on it. So these kind of work hand in hand, number 1 and 2. And then this quote by Singhi is funny. He says something like, relativists are in this ivory tower. And most people would take that to be a kind of argument against working with or being a relativist. But he likes it. So he's like, yeah, we're in this ivory tower. And he sees the goal of science as understanding and conquering. And he thinks that we're just in the understanding phase for now. The conquering will come when we have empirical predictions and like a handle on how to control it. But he's totally fine being in the ivory tower of understanding. And then again, we see Kannefig echoing the same idea: extreme paucity of experiments whose results require GR for their correct interpretation. Okay, and then another smaller reason that I want to highlight from Van Dongen is that Einstein isn't actually helping very much with this whole story. So you might think, well, maybe Einstein can encourage people or relativists and develop out the community. But actually, he's pretty concerned with promoting or trying to find a unified field theory. So he's not really in the business of trying to promote GR and encourage folks to work on it during this time period. Okay. And then I'll just note, like, there's also really low-hanging fruit in quantum mechanics where a lot of the physicists are actually working in. And so it's hard to justify working in GR when, there's low-hanging fruit, empirical results, and really interesting stuff going on in quantum mechanics next door. Okay, so that's kind of to set the stage of where the low, or why the low watermark period. And so now the question is going to be, where did the revival or renaissance of GR come from? And then how does that play in this full story with exact solutions? Okay, so there's a 1955 conference in Bern, which is the 50-year, in celebrations of 50-year of relativity. The 50 is tied to special relativity's publication at the time. And it's also the year that Einstein passed away, like just before the conference he was supposed to attend. So it ends up being kind of in memorial as well. So this is in Bern, Switzerland. And it starts to mark a shift in interest and people becoming more interested in GR. So I'm going to focus on the US context, as that's also been most of the focus of the literature. But I'll also note that Alessio Rocci, we just saw a presentation, some of us from him in Athens, on the European context. So the European Space Research Organization's role in the revival. And then I'll also point to Narlikar's chapter in Astronomy in India, Historical Perspective, for some discussion of the underexplored Indian context where results are being derived and then Europeans are rederiving the results and then publishing it, and only now do we know that they were kind of already had been derived. Okay, so why is there a revival? So Shield thinks that this is partly because new terrestrial experiments are becoming possible. So he has in mind something like the Pound-Repke experiment. So that's part of the story. Kennefic attributes it to advances in astrophysics. So he ties this to some of the interest in radio astronomy and quasars and pulsars and how GR might contribute to understanding those. This doesn't actually end up panning out for GR, like it doesn't have much to say about quasars and pulsars, but they thought that it might have more to say, and so people began pursuing it. And of course, there's interest from the US Air Force for space exploration and Cold War applications in GR, you know, regardless of whether they really understood what they were funding or not. There is funding going into it from the US Air Force. But the part that I want to focus on that is perhaps a little bit underappreciated in the story is the role of private donors in this story. So there's, after the 1955 conference, there's a series of conferences that happened that got dubbed GRN, where the first one is GR0. This is GR1, so this is from a 1957 Chapel Hill conference. And in this, you'll see this guy, Agnew Banson, and a quote from him: "No man lives long on this earth. It will take the concerted efforts of many men to pry forth one of the deepest and most obstinate, but one of the most important and potentially useful secrets of nature. In this quest, we are reaching for the stars and beyond." Published sci-fi author of The Stars Are Too High. I suspect nobody has heard of him. Has anyone heard of him? You guys are like, why is this guy being quoted? Why is he being quoted in the proceedings of this conference? So that's what I'm here to explain. Okay, so in the paper, The Price of Gravity by Kaiser and Rickles, they say a significant part of the work that blossomed into the renaissance of relativity in the 60s emerged from networks and institutions that were sustained primarily by private patronage. So their argument is that despite the surge in federal funding for basic research, gravitation actually remained a pretty low priority for federal officials amid wartime mobilization and other stuff going on with the early Cold War. So actually, they argue that private donors played a critical role. So who are these private donors? The first one is Roger Babson, who ends up being the founder of the Gravity Research Foundation, which has run an annual essay competition starting in 1949. And in 1949, the prize for the essay competition was about equivalent to the annual salary of a postdoc, a physics postdoc. So like, it's actually a pretty significant amount of money that they were winning. And this essay competition is lasting today. So they're still announcing winners today. So Babson is interested in this topic because he's interested in pursuing anti-gravity. And he blamed gravity for the drowning of his sister when he was young. And he has this essay, "Gravity, Our Enemy Number One." So he wants to pursue research on gravity in order to, I don't know, get back at gravity for the drowning of his sister in an unfortunate accident. And then also in this essay, he talks about like how he wants to have a display of birds in the Gravity Research Foundation because birds are able to conquer gravity. Okay, so he claims also to have used Newtonian gravity to predict the stock market crash in 1929. So he's like a big entrepreneur and also has this kind of personal story of why he's interested in this. Andrew Banson, who's the one that was quoted in the conference proceeding, he goes to one of the conferences put on by the Gravity Research Foundation, and he meets Bryce and Cecile DeWitt there because Bryce DeWitt had just won the annual essay competition. So he starts to correspond with Bryce and Cecile DeWitt. They get John Wheeler involved, and they start the Institute of Field Physics in 1955 at Chapel Hill. Now, you might be wondering, why did they choose Chapel Hill after all this? So I didn't say, but the Gravity Research Foundation is based a little bit outside of Boston. So Benson had traveled there, but he's actually originally from and lives in North Carolina. He has an AC manufacturing firm based in Winston-Salem, North Carolina, but he's an alum of Chapel Hill. And so he ends up bankrolling the second annual GR conference in 1957, together working with the DeWitts and John Wheeler. Okay, so that's how he ends up, and his science fiction ends up being quoted later in the conference proceeding. So all of this is to say that there's a surge in interest in GR, and I think one of the thing I want to highlight is that interest in exact solutions comes from the surge in interest in GR. And, you know, part of this story is detailing the kind of chronology of where this ends up going. So in 1962, there's this paper, Exact Solutions of the Gravitational Field, by Ehlers and Kunt in the compilation Gravitation and Introduction to Current Research. So this, I think, is the first that I've been able to track, the first systematic study of exact solutions in GR, kind of combining different efforts from various folks. Then we have Exact Solutions in Field Equations by Kramer, Stefani, McCullen, and Hertz, first published in 1980, and then we get a second edition in 2003. That's like a pretty massive book. And then we have also Griffiths and Podolsky in 2009 have a systematic study called Exact Spacetimes in Einstein's GR. So we see this in the 60s and beyond. So we see this coming out of the renaissance of GR. We can also ask, like, what enabled specifically systematic studies of exact solutions for GR? Okay, sorry, table that. Let me give you a quick Ehlers and Kunt quote from this paper. They say, recently methods have been developed to construct more solutions than can be thoughtfully studied in a reasonable time. At present, the main problem concerning solutions, in our opinion, is not to construct more, but rather to understand more completely the known solutions with respect to their local geometry, symmetry, singularity, sources, extensions, completeness, topology, and stability. So basically they're saying it's pretty cheap and easy to come up with new exact solutions. What we really want is better physical understanding of what's going on in these exact solutions. And this same idea recurs again and again in all the books that I showed you that are systematic studies. Okay, so now I'll go into how it was, how they actually were able to systematically study the space of exact solutions. So they describe 4 different ways of constructing exact solutions. So the first is to use special coordinates. So here you can choose coordinates in which the metric takes a nice simple form and then solve the resulting field equations. So something like what Schwarzschild was up to. Ehlers and Kunt describe this approach as somewhat ad hoc because you're choosing a special kind of coordinate system. You can also use special symmetries, so you can assume the existence of some kind of isometry group with a specific structure and orbit geometry and solve the field equations subject to those symmetry requirements. Something like what Petrov was up to with the Weyl tensor and the classification of the Weyl tensor. You can use special null congruences, so assume the existence of a distinguished null direction or family of null curves, satisfying specified geometric properties, and then solve the field equations with that assumption. Something like what Robinson and Troutman were up to. And then finally, you can use curvature expansion, so perform power series expansions of the curvature tensor, and then sum up what you get to get the metric, something like what Penrose was up to. So these are 4 different ways that they kind of classify how to generate more exact solutions from your starting point. Okay, so despite the call to better understand these solutions, not much progress seems to have been made towards this end. And so I mentioned that you see the same kind of worries about the physicality of some of these exact solutions coming up in later books. So here's Griffiths and Podolsky saying, apart from a few familiar spacetimes like Schwarzschild, Keres, Friedman, little more is widely known about such solutions than that they exist and can be expressed in terms of a particular line element using some standard coordinate system. It appears it's much easier to find new solutions than it is to understand it. So they say the opinions of Ehlers and Kuhn thus indicates an even more urgent task as late as 2009. Okay, so what I want to argue here is that we're seeing a shift where new mathematical techniques are definitely shifting how people are thinking about and pursuing exact solutions. And the example I want to highlight is one that has been called successful, but also remains pretty baffling to this day why it works. And so I want to present this as a kind of example of one of the tricks that's being used to generate new exact solutions. It's the Newman-Janus, sometimes called trick, sometimes called onslaught, sometimes called algorithm. So just to show you like some quotes about some other people discussing this. So Bambi and Modesto, as late as 2013, say, Newman and Janus couldn't give a true explanation of the procedure. Drake and Sudarki say, however, no clear reason has ever been given as to why the Newman-Janus algorithm works, many physicists considering it to be an ad hoc procedure or fluke, not worthy of further investigation. Dalrajan, in a dissertation that he worked on with Matt Vitzer, says, no one has fully understood why this method works, and most physicists consider it to be an accidental trick. There are some that believe it to be a clue to deeper structure. Okay, so what is this trick? So let me give a little bit of background. We're going to start again with the Schwarzschild metric. So start with the Schwarzschild metric, describing the gravitational field around a static, non-spinning, spherically symmetric mass. We'll call it the black hole. Also, I'll just introduce that the Kerr metric describes the gravitational field around a spinning black hole. It's discovered in 1963, so quite a long time after the Schwarzschild metric. In 1965, just 2 years later, Newman and Janus develop a complexification method that will allow you to derive the Kerr metric from the Schwarzschild metric. So you start with the Schwarzschild metric, you apply their ansatz, and you get out the Kerr metric. So how does that go? So our starting point is Schwarzschild metric. What we're going to do is express it in terms of a specific set of coordinates. In this case, it's the outgoing Eddington-Finkelstein coordinates. And that will allow us to avoid a blowup of the Schwarzschild time coordinate at the event horizon. This coordinate system is adapted to outgoing null GD6. We're going to allow the coordinates to take on complex values. So that's the complexification part of the story. So we're going to choose a particular analytic extension where 1 over r goes to 1 over r plus 1 over r bar, r squared goes to r bar. And then you're going to perform a complex coordinate transformation where r goes to r plus ia cos theta. Finally, you re-express the metric in terms of the null tetrad components, and you end up with the Kerr metric for an axially symmetric, stationary, spinning black hole. So the story is you go from Schwarzschild, you start with Schwarzschild, you do some weird stuff with complex coordinates, and then you end up with the Kerr metric. And the question is like, why does that work? How do you go from something that isn't spinning to some weird stuff that you don't really understand what was going on in complex space to something that is spinning? And the key move is to allow the coordinates to take complex values using this particular analytic extension. Okay, so I'll pose some open questions, some questions that maybe you have upon seeing this presentation of the Newman-Janus trick, and then try and address them. So the first is, can this be replicated to derive new exact solutions? The second is, why that particular complexification? Like, there's a lot of different ways that you could have complexified. Why did that one work? And then thirdly, why does using complex coordinates in the first place get you new solutions in GR? Okay, so I'll try and address these. So first, yes, you can use it to derive new solutions. So here's a little bit of the story of what happens with the Newman-Janus trick. So in 1965 is when it's first published. They call it a, quote, curious derivation of the Kerr metric. Newman worked with some other folks to derive charge Kerr from Rieser-Nordstrom using a similar trick in 1965 as well. Damiansky and Newman derive Kerr-Nut from Schwarzschild. Gerses and Guernsey in 1975 offer what they call a kind of explanation of the trick. Drake and Sazarkis published an explanation of the trick again in 2000, clearly unsatisfied with the previous explanations. There's a bunch of somewhat unsuccessful attempts at using it to generate interior Kerr that will smoothly match the exterior. And then I'll end the story with this paper by Azrik Aino in 2014 that tries to offer generalization and explanation of the algorithm. So a history that's littered with attempts to explain something that later people say weren't actually good explanations of why the trick worked. But also clearly in this story, we see extensions and reapplications of the trick to other kinds of contexts. Okay, so can it be replicated? Yes, we saw examples of how it got replicated in other contexts. What's the significance of the particular complexification? This is maybe the hardest question to answer, and one that I think really only got a good answer with Azrik Aino's papers on this. So he offers a generalization that shows that you don't actually have to pick a particular complexification of the R coordinate as Newman and Janus did. Rather, it only requires that the metric be able to be put in Boyer-Lindquist form, which is the idea that there's only one off-diagonal component, and the requirement ensures that you get a black hole solution within the Kerr family. So for those unfamiliar with like the terminology here, the takeaway is just that the particular complexification didn't seem to matter as much as it originally might have seemed. Rather, it's part of this bigger family of it's part of this bigger story that it keeps you within the same family of solutions. And then the third question, how does using complex coordinates allow you to derive new solutions? So this goes somewhat hand in hand with the previous. The idea is that we're capturing something about the linearity of the field equations for a Kerr shield geometry. So Gerses and Guernsey write that complex translation is allowed in GR when you can find a coordinate system in which your pseudo-energy momentum tensor vanishes or Einstein's equations are linear. This is of course not true for an arbitrary metric, but happens to be true for the algebraically special Kerr shield geometry. And so the way I would phrase it is what we're doing is we're taking real slices of a complex space of solutions. And so what you're doing when you're going into complex space, you move around in the complex space, and then you take another real slice. So the trick is allowing you to move from a real slice to the complex space and then come back down. That's the kind of general idea I have. And I think this is largely analogous to other kinds of applications of complexification in physics, where we imagine complex numbers rotating us around the space of solutions. So maybe this is just to say there's nothing mysterious going on with the complex numbers. Rather, it's something about the feature of the solutions that allows one to move around in the space using complex coordinate translations. Okay. So the moral of this story is that when it was originally proposed, it had not very well understood justification, and yet there was huge uptake. There was a lot of reapplications of the method without really good grounding of why it seemed to work. And, you know, depending on who you ask today, some might say, we still don't really understand why it works. And I'd say that this episode illustrates a shift in methodology and approach. The goal isn't examining exact solutions as representations of the actual universe anymore. The best way that I've been able to think about it is that they're being used as kind of bits of structural reasoning. And here I have in mind Lydia Patton's paper, like fish bones, something, idealization, structural reasoning, in which he discusses the role of heuristics in structural reasoning and how idealizations work in that context. So these are kinds of bits of structural reasoning that we think that they provide us with good heuristics for theory pursuit and application, but they're not like direct representations anymore. And I think this helps us understand why the authors of books about exact solutions continue today to lament that those exact solutions aren't being really well understood. Like, the goal was never to understand exact solutions in and of themselves, but to understand the theory space. And understanding the theory space allows you to kind of capture these structural reasoning components in pursuing the theory. And so the upshot is that the fact that they're idealizations doesn't actually seem to matter at all. Okay, so I should have 2 more slides of discussion. So reflecting on this whole revival or renaissance of general relativity, it seems like there are definitely new mathematical tools like Petrov's classification scheme that are necessary to begin studying exact solutions in a systematic way, for sure. And then once there's enough interest and the community has grown, exploring the space of exact solutions becomes a tractable and rewarding project in and of itself. And techniques like the Newman-Johannes trick become valuable because they allow you to move around in that space of solutions, regardless of whether you fully understand why they work or what they're capturing in the underlying theory space. But I want to emphasize a few things. First, that the role of exact solutions is clearly changing from the 1920s to the 1960s. It's being expanded, and seeing individual solutions as models of the world is definitely still the case, but also the space of solutions has become an object of study. And if you think that private patronage was critical in the renaissance of relativity, I will argue that private patronage also had to play some role in the changing understanding of exact solutions. To some extent, it enabled a sufficiently large body of folks doing relativity to support the idea that we could study systematically the theory solution space. Okay, thank you.
Helen, do you have that? All right. There's a questions or hands. This is first. Third.
Thank you. That's great. This is a more general philosophy of maths question than philosophy of GR question. I'm interested in understanding how something like complexification could be seen as as an abstraction of a description onto a high-dimensional space, as against an idealization of some sort. So for example, if I can take a geometric object, I can rewrite that in some cases onto a topological space, it's high-dimensional space. I would not call that as an idealization. It's an abstraction onto a high-dimensional space. And so I'm wondering if complexification is an instance of abstraction onto a more general space, whether physical, non-physical, and maybe not an instance of idealization. Thanks.
Yeah, so in this context, it's a tool that you use for deriving new solutions. And I don't think that I could support something like you're reading, because it's not as if people do complexification and then work in that abstract space. They're then coming back down the real space. So I think I could only really support, oh, it's an abstraction to this idealized space, and then you do theory there, if I found evidence that anybody's actually like working in that complex space and thinking that that corresponds in some way to reality. But it seems to me to be this kind of bridging tool that allows you to derive real solution to real solution.
The bridging itself, which is maybe not a part of it's not a part of a high abstraction of that theory. Would just an argument of being like a pre-bridge be an artificialization? Still,
yes. Yeah. When I was thinking about this, that was a big question for me of like, what really is it doing? And I found the pattern stuff to be the most useful here, where it's like a heuristic reasoning trick as opposed to something further. So maybe we can talk more afterwards, but I find it hard to justify like thinking about it as itself a kind of abstraction.
have a finger on this, so Eugene. And I think it's the same question Didier has. That's why I'm putting it in. I I think part of the question is, at some point in the talk you said that this trick, it's no longer seen as a problem that it is an idealization and not physical. And I guess one could pose the question is whether that is the right kind of thing to be an idealization, right? So when you mean that, like, you probably meant then, like, given your response, the resulting metric that you get when you come back from complex number space, right? That they're not worried about whether that representation is an idealization. What is the candidate for being an idealization at the end of, like, in the latter part of your talk?
Well, my point is that we're no longer thinking about the metrics or exact solutions as idealizations of the world. We're thinking, let's move in the theory space to explore what the theory structurally tells us about the world.
Yeah.
Did that answer it?
Yeah.
Okay, great.
Yeah, so I just want to understand the role of this complexification trick. I mean, it's a common move all over math to go to an analytic extension. There are just certain problems. If you're interested in a problem in real analysis, sometimes it's just easier to move to complex analysis, solve it, and then get the real solutions. And in fact, it's a theorem that complex analysis is a conservative extension of real analysis. I mean, is that what's going on here? Basically the same sort of move that people make all. In fact, complex numbers were invented to solve cubic equations because you can just write down a formula for solutions of cubic equations, and if you're only interested in real solutions, just discard the complex ones.
I think no, because it's not as if you didn't know the solution, so you've moved to complex space to figure it out and then come back. It's like you knew the solution. The complex space allows you to perturb it maybe, or like find a close by one and then find that solution again. So I think the role is slightly different than that. It might be akin to, like, if you were to, like, with rotate to get a new solution or something like that. So you're using,
Okay.
Great, Helen. This is super interesting. I learned a lot. I was just wondering, at this specific question about why the complexification works and why, like, moving back to the real, like, the solution space, it all, like, recovered back to the chaos strategy geometry. I think, like, maybe the justifications can go in different ways, not only in that, like, because calling for the justification or explanation for the specific technique might be very difficult because the real justification might not come really from how you do the mathematical trick, right? It has something to be related to, like, the no-hair theorem and the reason why the chaos structure geometry is the kind of attractor in the universe. And then it has to do a lot of, like, perturbation of the class of solutions that we are interested in, the exact solutions. And yeah, so that's back to your point, maybe, because you talk about the code from the Comte, that they said, well, the importance of starting exact solutions also about the symmetries and also stability at the end. I think that part is very interesting and important, right? Because that kind of provides a justification of why the solutions that they all, like, complexification come back are really the kind of attractors. That's my simple thoughts, I think.
Yeah, that's great. So I think a large part of why people were unsatisfied with previous explanations is because they take the form of, like, this complexification just moves you in the same Petrov class of solutions. Like, it keeps you within this class. And people would be like, yeah, but why does complexification work? Like, you need to tell me more than that. And I think that this Dalrajan quote is like, you're looking for the clue to deeper structure in understanding why it would work in the first place. And until you get something that tells you something more than what you started with, that goes beyond just the mathematical explanation of the trick, you're unsatisfied with explanation. Yeah, so I think that's right.
And the second question, if I may, sorry.
Thank you. This was super interesting. I'm just trying to better understand what the Newman-Janus trick gets for us. Like one question I have is was this ever used to derive new solutions, or is it only ever connecting solutions that we already know?
Mostly from known to known.
Okay, well then given that, one of the things you said earlier in your talk is that we have all the solutions we want. The problem is not getting new solutions, it's understanding features of them, their symmetries, extensions, topology, and so on.
Yes.
Does knowing that two solutions are connected through this Newman-Janus trick, this rotation in complex space, does this give us any information about the features of particular solutions? And then maybe more broadly, if not that, what does learning about the fact that solutions are connected in this way tell us about the world, if anything at all?
Yeah, this is a great question. And it's generally about like, what does exploring a theory solution space actually teach you? So I would say that until you get the kind of explanation that Eugene is after, with like the kind of bigger picture lesson of the underlying reality, you don't really get further information from the Newman-Janus trick, because after all, it's moving you between known solutions. But if you are able to get that more fundamental understanding of why it worked, it does tell you something about the overall space of solutions. And in this case, it's kind of taking out, like, partitioning a kind of space in that larger solution space, that you then understand why those solutions are kind of connected together in some way. So then if you were to think like, okay, if I'm developing future theory, I will have to kind of accommodate for the particular connections I find between these kinds of solutions. In general, I think people want understanding the solution space to be useful for future theorizing. Now, I don't know, in that bigger pursuit, if actually understanding a theory solution space helps you for future theorizing. It is a kind of task that you can do in the space of your idealized models. But as for whether it actually will help you, I don't know. It's clear that the first way of understanding, where you're like working with the Schwarzschild solution and understanding whether as an idealized model, what parts of it correspond to the world, that for sure does help for future theorizing. But the question of whether moving amongst solutions in your theory space does or not, I think is still somewhat open to me.
Sorry, this is just a comment, because I fully agree that it is true that in the original context that Helen discussed, Newman-Janus tricks takes us from known solutions to known solutions. But kind of like recently, there's been a lot of work in theoretical physics where people kind of use the modified version of Newman-Janus trick to generate new classes of solutions.
Yeah.
And that happens with like regular black holes, with black hole bounce spacetimes, and it's quite remarkable that you could have like a non-rotating black hole, use the weird Newman-Janus trick, and then get like a rotating thing out of it. So then it arguably could be seen also as a solution generating technique, but the caveat is that some of it requires some modification of the already very confusing algorithm.
I guess another thing to say is like, when you understand the generalization, you can then try to derive novel solutions in a way that you couldn't have done before, because you didn't fully understand why it worked. So you were worried that if you applied it to a new solution to generate, or if you applied it to a known solution to generate a new solution, you weren't really going to be sure if what you would end up with is anything reasonable.
No, I have a opinion.
Like one example for that question is like, once one understands one specific exact solution very well, like including the geometry, the conformal like diagram of it, and all the related properties, and then one can do for like future theory. For example, there's a new model like black to white hole transition, which is a quantum gravity model of like using charged black hole or the Oppenheimer-Schneider. So that because you know how to stretch around the solution so that you can apply it in a multiple context and you get something new from it. And that's based on how you understand very well one particular solution. Oh, yeah.
I'm gonna ask two questions. Take that.
Wow.
So I have two interrelated questions, and I'm no physicist, so help me here. One is, I wonder what is happening in a certain kind of way is we're starting out with this thing that people are calling kind of ad hoc. And once we change this perspective as to what's going on, it's not really an ad hoc, it's a perfectly rigorous thing that we're doing, but doing something different. And the reason why I'm asking that is I'm trying to figure out in what ways this kind of story is analogous or disanalogous to the only other thing I know in physics, which is perturbative renormalization and the relationship that has with renormalization group methods, where we start out with something that early in the 20th century was like, oh, that's dippy. And then later in the 20th century, we're like, that's not dippy anymore. But it also seems to involve something like we can treat a problem using this other theory in that theory space and we'll be fine. And it seems like there might be a parallel there, but I don't know if that's just a surface similarity or not. So,
Okay, we should talk more about the particular case. I guess I'd just say that it can look, I mean, I would still think that people reflecting on the history would say that their choice, Newman and Genesis' choice, was ad hoc, but that we can understand better why that ad hoc choice worked with developments since then. So I think, yeah, there's definitely plenty of examples where that is the case in various like fields of physics and beyond, where things that looked ad hoc got explained as part of a bigger picture story of what was going on. The question is just like, what are your standards for explaining why that ad hoc thing worked? And just, you know, like looking at the history of different kinds of offered explanations, it seems that people have very different standards for what would count as an explanation. And it seems like maybe the thing to say is, if that's all the explanation you can get, then okay, fine. But perhaps there's something deeper. And on occasion, people are trying to pursue the something deeper and offering that as an explanation. I don't know if that answers. Those are two.
Okay, so sorry. Now I forgot my question. So I suppose my question is related to what Eugene is saying. I'm just like not sure about the more involved applications of GR, but like I think it's related. So I guess I'm thinking about the empirical applications of having a solution space that you understand well and that is varied, right? So I'm like my thought example here is like the person who does this first really in the history of physics is Newton, who derives like a whole class of centripetal force laws. And the reason that he does it is that when he considers the empirical evidence, such as the Keplerian orbits, he can check whether they uniquely support the inverse square law in a way that he couldn't without the wider class of solution space, because then you can reason about the uniqueness properties. So the inference there is going from the empirical evidence to the theory, and that the value of the solution space is that. So it's not necessarily, I don't know, a theory of quantum gravity that we eventually develop or something like that. But it's thinking perhaps, okay, what is the right solution for our universe or for this particular object of study? And yeah, I guess that is my question. So I wonder whether you could speak a bit about the way that it's not just the exploration of the theory space is also used when we're thinking about empirical confirmation in this context.
Yeah, good. Okay, maybe I'll say two things, and I'll try and remember what the two things are. So the first is that unlike that case, I think this case is one in which, because you don't understand these like important things you would have to understand to make the connection to the empirical side, it's harder to get that kind of argument off the ground. So you might say like, okay, maybe what they're doing is like exploring the solution space so that when you then do like observations of a black hole, you can tell which of the exact solution seems to match onto your observations. And like to the extent that that argument works, totally grant that that is going on. I think that's a very limited range of the solution space, and really you don't actually need to do much exploration of the theory space in the way that these like giant volumes that go through systematically the different kinds of options in the solution space do. And if you don't understand these kinds of things, then you're definitely not going to be able to understand what the empirical consequences of that particular solution would be for your black hole observation. The second is more broadly, I've been thinking about what the role of explorations of the theory space are, but in a very different, like in the cosmological context, and where you're trying to understand like what the solution space of, say, alternative models of gravity or dark energy and dark matter might be like. And there, like sometimes the solution space is so both constrained and like all of the theories seem to have to recover the same empirical predictions in a way that actually maybe exploring the theory space isn't doing as much for you as you would have wished. You're exploring the theory space because you have to recover the same empirical predictions, you have vast undetermination in like models of what could be possible in the universe. And so you might have wished that exploring the theory space would let you better understand which of the models is viable, but because they all have to recover the same thing, it's not actually serving that role. You need a little bit more like an unconstrained exploration of the theory space. But yeah, we can talk more about.
Oh, super interesting. Okay, I think we have time for one more question if there is one.
I think Eugene had question 2.
Oh yeah, you get the second.
Yeah, no, just I want to like hear your thoughts about, because this is a study of the period, especially from 20 to 60s, like during the low water mark. But like I think there's a very potentially interesting story to tell about the role of exact solutions in numerical studies, and then all the way to like the very important work that we recently have about black hole image, so that how much importance of the exact solutions play in the numerical physics, like even between the collaborations between Russians and Americans, so that they develop such and such techniques that would be very important in the HT. That would be super interesting.
Oh, my response is short, and then it's just that I haven't looked at that. So I can't speak to that maybe yet, but it is a very interesting kind of application and much more empirically motivated than this. Thank you.
Final word goes to Eugene. No, Helen is running to Eugene.
And Helen will get a final word. It's kind of a question about, I guess, the role of exact reasoning here is, and maybe how I was wondering how you thought about how this kind of exploration of exactness and its perturbations in complex space. How do you think? How will you understand its success or lack thereof compared to the later efforts in studying exact solutions? And like, do you think there's like some reason or principle why the later methods work better, like post 60s, like the Penrose kind of style of examining the topological causal sort of solutions as opposed to this kind of complex space explorations? Is there like a reason, or do you think just like that's just how it happened? Like we just happened to find a nice new tool, new way of perturbing these exact solutions later on. Just wondering how equilibrium reasoning features here, I guess.
Yeah, I would think that the Penrose style stuff is much more robust as a new tool than the Newman-Janis trick is. I feel like the Newman-Janis trick is like quite limited in what it can actually do, and that the Penrose stuff has like both better underlying motivation and allows you to do much more. So I guess, yeah, it's a more useful tool in doing the kind of exact reasoning.
But kind of like,
Yeah.